factors involved in PCA are to standardize the range of continuous initial variables. This can be done in terms of centering or a full standardization. We then want to compute the covariance matrix to identify the correlations. We compute the eigenvectors and eigenvalues of the covariance matrix to identify our principal components. We then create a feature vector to decide the principal components, and we recast the data along the principal component axes. So our first example is about blood pressure. We have a data set on the left that compares systolic blood pressure to diastolic blood pressure. We note the mean of the first column is 129 and the mean of the second column is 82. So by simply subtracting the mean from the initial data point, we go and we center the data. So 126 is our first systolic blood pressure. Our mean is 129. 126 minus 129 is -3. Similarly, 78 minus 82 is -4. So we've centered 126 and 78 to be -3, -4. We do this for all of our data points. So the initial data points that were given are in the panel on the left. I've centered the data, and we can see what that looks like on the right. So the same general shape, I've just essentially moved the center of this into the center of the data. Next, we compute the covariance and variance matrix for the systolic and diastolic blood pressure data. We're then going to use this matrix to find our eigenvectors and eigenvalues. So we take this matrix and we subtract lambda I from that, and we get our eigenvalues. When we take the determinant, we get our eigenvalues by solving P of lambda equals lambda squared minus 12.4 lambda plus 3.84 lambda, or sorry, 3.84 equals 0. So our lambda are approximately 12.08 and 0.32. The eigenvector associated with 12.08 is V1, which is equal to 1 over 1.37. And the lambda associated with 0.32 is V2, -1 and 0.73. We normalize these vectors, and we get V1 equals 0.59 and 0.81. Vector 2 is -0.81 and 59. So our eigenvectors make up the columns of matrix V. So 0.59, 0.81, -0.81, 0.59. We have our matrix D, our original data that's been centered. And so DV is 2-column, 6-row matrix that's our original data scaled by vector V. We can also see in the diagram on the left, our first principal component is the red arrow that points to the upper right quadrant. Our second principal component is the red arrow that points to the upper left quadrant. And so that's how our data is going to be rotated. So on the left, we see our original diagram with our original matrix of vectors. We see our original data set that was centered. We can see that the variance here is 4.4 in the first column and 8 in the second column. Now, the total here is 12.4 units of variance. Looking down at the bottom of the second chart on the right, we can see that we still have 12.4 4 units of variance, but it's split up in a different way. Looking at the diagram in the top right, our data has been rotated 45 degrees clockwise. And as we saw earlier in this section, we could ignore the vertical axis in this diagram, which we've labeled PC2. The variance associated with PC1, the x-axis in this figure, is 12.080. The variance associated with the y-axis in this diagram, PC2, is 0.324, which means that the variance that we capture here is 12.08 over that 12.4, or 97.4% of the variance is captured simply by the PC1 component. So if we go ahead and eliminate, forget about PC2 in our future calculations, we're going to get 97.4% of the variance captured simply due to that one component. Here's another example. We have grades for 5 students in math, science, and arts. We're going to use these grades to try to do a linear regression on how these grades correlate with grades on a diagnostic test. So again, we begin by centering the data. So you have to find the mean of the math, the mean of the science, the mean of the arts. We can compute then the center of the center data. As before, we compute the variance and covariance matrix. And this is the matrix on which we're going to try to find our eigenvalues. So a little trickier in 3 dimensions to find eigenvalues and eigenvectors. But we do come up with a polynomial, p of lambda, which is equal to negative lambda cubed plus 1980 lambda squared minus 1,002,375 lambda plus 50,118,750 equals 0. Solving that, we get 1,137.59, 786.39, and 56.02. So our first lambda gives us an eigenvector of 1.06, 0.69, and 1. Our second lambda gives us an eigenvector of negative 0.5, negative 0.68, and 1. And our third lambda gave us an eigenvector of negative 3.75, 4.28, and 1. We normalize these to be V1 equals 0.66, 0.43, 0.62. V2 is negative 0.38, negative 0.52, and 0.78. V3 is negative 0.64, 0.74, and 0.17. Going back to solving the polynomial, when we have something that's larger than degree 2, we're typically going to use some sort of equation solver to find the roots. Don't think that this is something that we're going to do by hand. Okay, taking those eigenvectors, we can form our matrix V. And so V is the matrix 0.66, 0.43, 0.62, negative 0.38, negative 0.52, 0.78, negative 0.64, 0.74, 0.17. We multiply D, our original data, by V, and we get our matrix DV. We know that the total variability in this data set is 1980. So PC1 captured about 57% of that, taking the eigenvector, dividing it by 1980. PC2 captured about 39.7%. So overall, PC1 and PC2 capture almost a little over 97% of the data. So how can we use this? Well, it might seem like a fun trick to be able to reduce the dimensions of our data. This actually has a lot of really good uses. Image compression is obviously one of them. We saw in previous examples that we could take something that had hundreds and hundreds of dimensions and reduce it down to something that was a small fraction, maybe 10% of the dimensions. To give you a more tangible example, we did a linear regression here with the math, science, and art scores against the SAT scores that the student got. The SAT score I did as a weighted average of math, science, and art at about 15 parts, and 1 part randomized between 0 and 1. Right, so 15 parts math, science, and art, and 1 part random. So there should be a very good correlation between the math, science, and art score and the SAT score. So I ran a regression, just a standard regression with the original data, and I got y equals negative 63.69 plus 4.99 times the math score, plus 5.78 times the science score, plus 5.2 times the art score. And that gave me an adjusted R squared of 92.9. If I run the same regression with principal component 1 and principal component 2, I get something that looks like negative 36.83 plus 9 times PC1 minus 0.3 times PC2, which gives us an adjusted R squared of 0.962. Now, comparing those first two, I told you that I used equal parts math, science, and art. And that doesn't seem to be reflected that well in our first linear regression model. In particular, math takes 5 parts, which is a third of the 15 parts that I used to make math, science, and art part of the score. But it uses almost 6 science and 5.2 arts. So in fact, the normally distributed noise that I put in there is actually messing this up a little bit. Using only principal component 1, I get a little bit better adjusted R squared. Now, part of that has to do with the fact that I've got 1 fewer variable. But you can see that the contribution that's made by PC2 is very, very small, only 0.3 compared to 9. So principal component 1 adds the vast majority speaks to the vast majority of the variability in this model. If I use principal component 1 only, I get a model that looks like y equals negative 26.44 plus 8.98 times PC1, and that scores about a 97.9% adjusted R squared. And you can see that in the diagram using principal component 1. So we've gone ahead and we've reduced from 3 variables or 3 dimensions down to 1, and we get a very, very good approximation of the scores on this diagnostic test. Now, I'm not going to pretend that 3 dimensions is too many dimensions in this case, but again, think about something like image recognition, where you're dealing with hundreds, sometimes thousands of dimensions. Reducing it down to a small fraction is going to save you a lot of time when you're processing that information.